Okay, I believe it is time to start. So my name is Ulf Norell, and I'm currently at Gothenburg University in Sweden, where my job is to make this nice language that you might have heard about, which is called Agda. And today, and 3 other days, my plan is to teach you some of what you can do in Agda. And we're going to focus on programming in Agda. We're going to write some programs. But before we get to that, I just wanted to show you this page here, which is where all the stuff is. So it's on GitHub under my username, Agda Summer School. And the important bit, well, you need to download this, of course, but there are some instructions how to get started up here. Installing Agda. So there have been some issues with installing Agda on Mavericks specifically, because Apple broke GCC. But I believe by now there are a few people in the room that are experts on how to fix this. So you can ask around if you run into problems. So what I was just going to show you was this bit here. So once you've got the summer school repo downloaded, there's also a library that I made for the summer school, which is called Agda Prelude, that you should download and install. And then you have to set up the path to Emacs, which you do by saying customize group Agda2, and then the second option is include directories, and there you should have, well, obviously not that path, but to wherever you put the Agda Prelude. And so yes, there should be 2 lines. You should not forget the dot, the current directory, because if you do, then you won't find the file you're working on. But this is what it should look like. And once you've done that, you can open this lambda.agda, which is in the exercises directory, and type check it with Control-C, Control-L, and compile it with Control-C, XC. And that, if everything works, should give you a binary lambda that you can run on this little lambda turn that I've defined, which adds successor to 52,000 something a bunch of times. And if you run it, it prints the desugared parsed lambda term, and then it prints the result of running that term through the SECD machine. So this is going to be what we will play with this week, starting tomorrow. So today we'll do some warm up stuff, and then we'll get to lambda calculus tomorrow. Okay, so as I said, we're gonna focus on actually writing programs. So that's going to be the main objective, and we're going to use dependent types to make programs nicer. If we find out that adding dependent types, we have to prove a bunch of lemmas or things like that, we're not going to bother. Right? We're not here in this module to write any proofs. In fact, I don't think we're going to write a single proof. I might be lying, but that's certainly going to be the goal. So we're just going to add dependent types, use dependent types in our programs to get some help from the type checker to make the programs look nicer and things like that. Also, I'm going to show you a bunch of examples, and I'll try to introduce the various pieces of syntax, but I'm going to forget. So when you see some piece of syntax you don't understand, interrupt me and I'll explain it. So the example I'm going to do first is this is basically the hello world of dependent types. We're going to build a tagless interpreter for a super simple expression language. So first I have the completely untyped, what you could write down in ML or Haskell or any sensible language. So we have expressions. So I'm declaring a data type here. Set is the type of Agda types. So I'm saying expression is a type, and here are the ways to construct an expression. So there's a constructor lit, which takes a natural number and gives you an expression. True and false are expressions. There's a less expression, which is supposed to compare to natural numbers, and adding natural numbers, and there's an if construct. So I've named some of the arguments here. So this is the dependent function type. So it takes three expressions that we've called A, B, and C, and then it gives us an expression. And I didn't actually have to name them because we're not using them. I could mention them over here, but in this case, I'm not. So I could have written this as just exper arrow exper arrow exper, but that's like 5 characters more, so I didn't. That's an excellent question. So Agda does Unicode quite nicely. So you can have Unicode characters in your identifiers, and I will have that occasionally. There's a mode in Agda. So you type / and then some characters that identifies what it is you want. Mostly those are the LaTeX names. So if you know the LaTeX names, you'll be fine. There's some exceptions, yes.
If you type metax Agda input show translations, you'll get a buffer that shows you all of them.
Oh, cool. I didn't know that. Thank you. You can also do so. This I've made a little Emacs cheat sheet that you can open. So it's under the summer school repo and then doc/Emacs cheat sheet, where I list a bunch of Emacs commands that you might find useful, and there's also a Unicode, where I've just listed, I think, the characters that I'll be using this week and how you type them. If you see a character and you want to know how to type it, you can do this magic incantation, and then you get a little window, and if you look carefully somewhere in the blob of information that's printed when you do that, it says how to type it in the Agda mode. Okay. Right, so this is the boring untyped expression type, and so what we want to do is we want to take one of these things and evaluate it and get a value. So if we want to do that for this type, it gets really painful. And I've tried to make it nice here, but it's still going to be painful, and we're not gonna go through the details. But basically, so we're going to take an expression, and then we should compute its value. Well, what's the value? Well, it could be a natural number or a Boolean, right? So I make a little data type for values, which is 2 constructors, nat, and then that takes a natural number, and bool takes a Boolean. And then the eval function, well, it might not be a well-formed expression, right? So we might not be able to evaluate it at all. It could be plus true false. That doesn't make sense. So there's no value we could produce. Well, we could add an error value to the type, of course. But I've chosen instead to define eval as a function from an expression to maybe a value. So if you're ML, this is value option. Right, it's either nothing or it's just an a value. And then, everything is fine for lit and true and false, but as soon as we want to perform an operation on values, we sort of have to handle all the error cases. So here's less than. So I've defined these auxiliary functions, get nat and get bool, which takes a value and gives us, if it's a natural number in the first case, gives you the natural number and nothing if it's a bool, and get bool the other way around. And then you can define, say, the less case quite complicatedly, right? So I'm using sort of magic maybe operators to sort of do the plumbing, and we're not going to, it's complicated. Yeah, if you didn't want to use these monadic binds, and this is fmap, and this is applicative apply, if you know your Haskell libraries. You'd have to case on the result of doing eval. Was it nothing, then nothing? Was it just? Is it just of the right type? This is exactly the sort of thing that we don't want to have to worry about. So what we're going to do is we're going to take this and delete it, because that was not nice. Right, so what we're going to do instead is we're going to build well-typed expressions. We don't want to worry about all these error cases. So let's just have expressions that are well-formed. So to do that, we need a notion of type. So an expression can be a natural number or it can be a Boolean. So we're going to make a data type for types. So a type for this language is either nat or it's bool. So it's a simple enumeration type. And then we're going to say, let's index our expressions by a type. So this, if you're familiar with Haskell, this will be a GADT. Otherwise, in Coq it would be an inductive, I guess. My Coq is not very good. So basically, what we're saying here is that we're defining not just a plain data type, we're defining a family of data types indexed by this type thing that I just defined. And then all the constructors obviously will have to be typed. So lit takes a natural number, gives us an expression of type nat. So that's good. True and false gives us expressions of type bool. Less expects two expression of type nat and produces an expression of type bool. Plus, kind of the same, except it gives us a nat. And so the first one will have to be x per bool. But the other two could really be any type, right? So I'm going to say for all t, x per t to x per t. So the for all here is really just sugar for a function type. So I could write this in this way. It would mean the same thing. Oh, I can leave that arrow there. We can remove between these named guys. You can put arrows if you want to, but you don't have to. So it means the same thing as this. The curlies. So notice you have parens here and curlies over here. The curlies mean this is an implicit argument, so it's going to be there behind the scenes, but really I don't want to see it when we're working with this type. So it's going to be hidden, and the type checker will figure out what value to put there. And writing for all, it lets me leave out the type, because it's clear from how we're using t that it needs to be one of those capital type things. So that types checks. Any questions so far?
Yeah.
Yes.
Sure. What do multi-line comments look like?
Like in Haskell, curly dash. Okay, let's see if we can get back to the evaluator and implement it a bit nicer. So the first question is, what should the type of the evaluator be? So before we had expert to maybe value. Well, we want to get rid of the maybe, but we still need some kind of value to return. So we still need a notion of value. But instead of making that a data type, we're just going to make it a function from a type, one of our object language types, to an Agda type. So what I did now was I put a question mark in the right-hand side, and then I load, Control-C, Control-L, and then it turns into, this is green. I don't think you can see it, but it's green to indicate that there's something magical going on here. So this is a whole, and in the whole you can do various things. So you can ask, for instance, what is the thing I have to prove, and what do I have to do it? So that's Control-C, Control-Comma. Control-C, Control-Comma. So these are all listed in the cheat sheet. So you should browse through that. Right. So I did that here. I asked, what do I have to give in order to complete this function, and what do I have in the context? And it says, well, the goal is set, and in the context you have this thing t, which is a type. Fine. What I want to do now is we want to pattern match on t, right? If it's nat, we're going to do something. If it's bool, we're going to do something else. So I type t into the whole, and then I hit Control-C, Control-C. Now it would be instructive if I could show you the right-click menu that's supposed to be here, but for me it doesn't work. On some systems, when you right-click in a whole, you get a little menu of options that you can do there. Fortunately, I know the shortcuts, so it's not really a big deal for me. But so I hit Control-C, Control-C here, and the system fills in the cases that I have to give. So we're going to go with for nat, a value for an expression of type nat. Well, that's just a built-in, a library, natural number, and for bool, it's just bool. And then we can write eval, saying for all types t, if you have an expression of type t, then you should be able to produce a value of type t. And hopefully we can now do this without any error cases getting in our way. So again, we want to make a case distinction on E. So I type in E and I hit Control-C, Control-C, and then it comes back with a bunch of cases. Control-C, Control-C. So Control double C. That's. So what we had, I had this. So you have E on the right hand side, and in the whole I've typed E. So you can do it on an empty whole, and then it'll ask you what you want to case on. It might, yeah. Okay, this is Emacs is a bit funny sometimes. When you undo, it thinks the buffer hasn't changed, so it doesn't have to write it again, but it has in fact changed. So anyway. Okay, so let's take this first goal here and ask, what is it we have to do? Well, we have to look at the goal now. The goal says nat. Right? We have to provide a nat. Previously we had to provide a value t, but in the lit case, t is nat. So value nat is just capital nat, which is just a number. And in fact, we happen to have one of those lying around. So let's use that. And the same for true and false here. We have to provide a boolean, a plain boolean. There's no wrapping of any kind, so we can just do that. Same there. I should say that as well. When you have something, you just want to give it, put it in the hole. That's Control C, Control space. We'll just insert whatever you typed into the hole. We'll just put it in instead of the hole. I put E and then Control C, Control C. Okay, so what about this one? This is the less function. We have two expressions of type nat, and we want to get a boolean. Well, we eval E and eval E1, and we check if one is less than the other. And that just goes. So and it works because the type of eval E and eval E1 is just nat, right? It's not some funny data type that we have to unwrap. It's just a natural number. I didn't put that in the cheat sheet, did I? It's \_1. Yeah, I should have done that. So Agda likes to name things with subscript 1, 2, 3. So in this case, it had two things it really wanted to call E, but it could only name one of them E, and the other one it had to name E1.
So why is less than like the decidable, computable less than and not a?
This less than gives you a boolean, but it gets the boolean by running basically Andrew's his ordered data type, where you get either a proof of less than or a proof of equality or a proof of the other way. And then it just checks, was it the less than case, and gives you a boolean back.
Does it use types to disambiguate different less thans?
Yes, this less than is overloaded. So there's a type class. We don't really have proper type classes in Agda, but there's a sort of a substitute for it that gets you pretty far. So basically what it does is when it sees less than, it says, do I have something of type ORD and the type nat in this case in somewhere in scope? And if it finds something with exactly that type, it'll do it. But it won't work for say if you wanted to compare lists, it would say, oh, I have this thing that takes an ORD A to an ORD list of A, and I have this ORD nat thing, but I don't know how to get an ORD list nat. So you have to do that by hand, introduce it. But yes, so this is overloaded less than. I guess you can figure out how to do the plus case. Works the same way. And if, well, that's just going to be an if then else on booleans. So if eval E, then eval E1 else eval E2. And we're done. So I don't know about you guys, but I like this one better than the one we had before. So this is kind of what I'm talking about when I say I want dependent types to make programs nicer. You know, if they in the process turn out to be more correct, fantastic. But the main thing we're going to be wanting to get out of our dependent types is to make the programs nicer. So any questions so far?
What's the meaning of having both the for all and the arrow quantifying?
So for in Agda, so as I explained before, right, for all is just sugar for an ordinary function space. But the for all construct is this, right? You're right. So these guys are part of the for all in a sense.
But I tried to do that here for the E, but that doesn't seem to work.
Well, no, because then you have to name.
Yeah, even if I do it, oh yeah, I forgot to space around the column again.
So if you can type this. So this means for all t of some type and e of type x per t, blah blah. So in Agda, we have many different ways of writing function types. Yeah.
Actually need the for all symbol, or is it, or can you just put? Because if I get rid of the for all symbol, then it looks like then it looks like it works fine.
Well, you have to give a type to t.
Sure. Yes, I do have a type for t.
So you could put in blank.
And now t is being declared as an optional argument to eval, basically.
No, it's not an optional argument. It's an implicit argument. So it's always going to be there, but you let the type checker worry about what the value is. Yeah. So the for all desugars to exactly this. Yes.
So how does it know the difference between, for example, if on the right hand side versus the if constructor?
That is an excellent question. There's some magic parsing going on. So if we look at the if over here? So that's also a useful thing I did. If you middle click on an identifier, it'll jump to the definition. So you can use that to browse through the libraries, and then it's meet as star to jump back. So the actual name of if then else is if underscore then underscore else underscore, and the underscores tell Agda where you put the arguments if you want to use this in when you want to apply it. You can also apply, use it as a function of that name, but you can, when you put underscores in names, you can use them in a mixed fix operator style. So here's infix operators are called underscore something underscore. So what happens in this case is that it's trying to parse the whole. So the first pass of the parser just it just parses a flat list of things, and then there's a separate pass where it tries to make sense of this as an Agda term, and then you could try to make sense of it as an application of if, but then you have these troublesome then and else guys, which aren't actually meant in scope, right? There's no thing called then that you could possibly refer to. And then it's going to say, okay, it's not that then, but we have this if then else operator, and we could parse it as one of those. So if I'd named this guy then and this guy else, then we would have been in trouble.
What would it have done?
It would complain and said, I don't know what this means. It could mean either this or that.
So it tells you if it's ambiguous.
Yeah. Yeah. So then it says, well, this doesn't make sense. Did you mean this thing or this thing? And obviously this is type correct and this isn't, but it doesn't do type checking to figure out what we meant. Okay? Right. Okay. So this was nice, but as expression languages go, it's kind of boring. Yeah. Because they're all closed expressions, and of course we want to have variables, right? So in order to do that, well, we're going to need a variable constructor, obviously, and it's going to take some representation of a variable, but it should be a well-typed representation, of course. So what I'm going to do is I'm going to go to Brown. So we're going to have variables are going to be indices into a context, basically. So context is going to be, a context will be a list of types, like so. And then I'm going to say expressions are going to be parameterized. So now I put stuff to the left of the colon, and that means it's not an index. We're not building a family over the context. It's just a parameter to the data type, like in Haskell or ML. You have lists of A, where A is just a parameter. And basically, there are two things that means. It means gamma is going to be in scope for all the constructors, and the targets of the constructors will have to have, the same gamma everywhere. All of them have to target X per gamma something. In the recursive arguments, yes, it can vary, and that's not going to matter today. But once we get to lambda calculus, then yes, it will. When you go under lambda, you want to change the context. Okay, so let's do that. And then put that in everywhere. What? Well, that was search replace. Most editors can do that.
I think you're missing a parenthesis.
Am I? No, it's checked. It's fine.
Get an X equals open parenthesis.
Well, I type checked, so I can't be missing anything.
C, sorry.
No. Yes. Okay, so here's another piece of syntactic sugar. When you want to for all several implicit things, you can just write the curlies once and then put a bunch of names. All right, so now we put the parameter in. We put the argument here in. Well, we're probably going to have some more stuff in eval, right? How do you evaluate a variable? We're most likely going to need some kind of environment to track values for the variables. But let's start thinking about the var case. So a variable can have any type. Oh yes, and now it's complaining about that. But we're going to need some argument here. Let's do that. So now we want, well, you could say, well, it's just a natural number, right? It's just a de Bruijn index of the variable, but there are a number of things that could go wrong with that, right? We could, we could have an index that's not, it's too big for the context, so you get a variable that's out of scope, or it could point out an element in the context that's not actually of the right type. So it's, if you have a context bool, 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 and you say, oh, and I have a variable of type nat, well, that's not going to work, right? There are only booleans in the context. So we need an index which is, well typed. So I'm going to define a type for that. I'll put a question mark. And then reload. Oh, that's weird. Some arrow missing, maybe? It does that as well. I quickly added a case for var, just to make it stop complaining. Down here. Right. So. When you reload, when you Control-C, Control-L, it should make all the question marks green. So it's. I mean, we've. Eval is this function down here that we're defining. So if it doesn't know about it, then it's because you haven't written it.
What is the first definition of eval?
It's here.
So here, I defined it here, and everything is
I mean, we're going to have a lab session after I'm done talking. So, if you get stuck, it's not crucial that you follow this example, or that you can type it in. I mean, we can do it. If it's not working, we'll look at it in the lab session. So anyway, I want kind of a natural number here, but I want more types on that natural number. So I'm going to define a data type which is kind of natural numbers, but with more types. And I'm going to call it membership, or \in. So it's going to take an implicit type A, a value of type A, and it will be a family over lists of A. And then our variable, so I didn't give any constructors, we'll get back to that. Let me just fill in what a variable is going to be. It's going to be one of these fancy natural numbers, and if you're proof inclined, you could read this as a variable takes a proof that the type is in the context. But of course, I promised we weren't going to do any proofs, so it's not a proof, it's a natural number. But it has some interesting indexing structure on it that will make it somehow perhaps look like a proof. So I promised it was going to be a natural number, so it better have two constructors, 0 and successor. So let's do 0. So 0, index 0, that's the first element of the list. So if I'm saying, basically what this says, x is in x's, gives you an index at which point x occurs in x's. So in this case, if the index is 0, well, then the first element of the list is going to have to be x. So this 0 is a proof that, and I'm going to need an infix declaration for this. 3. Yeah. So there's some noise here, but if you just read this bit, so we need an implicit argument, which is the rest of the list. But otherwise, 0 is a proof that X is a member of the list X cons X's. So 0 is the index at which X occurs in the list X cons X's. I mean, it might appear in other places as well, but at least it appears at the head of the list. What about successor? It's backslash double colon. Sorry, yes. Yeah, this is one character. So obviously, you know, the type has type is single colon and cons is double colon, as is the case in all sensible languages. But 2 colons is so wide, so there's a nice Unicode double colon, which it's too nice to pass up. I try to be kind of conservative when it comes to the Unicode, but not too conservative. So I mean, the in looks very nice, for instance, and double colon, it is a bit nicer. Okay, let me finish this and then we'll talk about it. So successor says, well, it's not the first element, it's another element further down the list. So the argument to successor, well, it takes the index in the tail and then it delivers the index into the list with one more element. So, or if you want to read it as a proof, then it says, well, if X is a member of X's, then it is also a member of Y cons X's for any Y. And we've got some implicit Y and X's that we don't really care about. They're just decorating the types there. Yes?
So if we are thinking of this as a proof, then is A in gamma the type of proof, the theorem that A is well typed effectively? Or that we have a type for A?
Well, I mean, concretely it says, you know, in gamma, which is a list of types, somewhere there's an A. Okay. Right? But that doesn't give you, if that was just a type, it wouldn't be a useful thing to have in the expression. Well, you could have, you know, in that case you would have the index separately, or you might have a name thing, and then you have the actual variable name, and then the proof that it's well typed. But now we just have the index.
Yeah, so here proof relevance is really crucial, right?
Well, if we had any proofs, then yes, it would be. But since we don't have any proof,
interpret it as proof, right?
Yeah, then this is not irrelevant at all, yeah. Right? It very much makes a difference. You know, if you have the context is nat cons, you know, just the list of nat, then var 0 and var 1 will be different things, and you know, whether you pick the proof that nat is in the list in the first position or the second position, it makes a difference. Yes?
Can you make that automatic part outward the list
Yes. It's awkward, but it's possible. But in this case, we wouldn't want to, because we care about the position. But it is possible to define decision procedures, and there's some reflection stuff, so you can do these things. It's just kind of heavyweight. Okay. That's good. That's good. So we defined the type now with a an interesting kind of natural number as to the Brown index. So we could start thinking about eval, and well, clearly we need something. We need some kind of environment, right? So here we have an index into the context, but what we need is a value. So we're going to need an environment, which is going to it'll have to be a list of values, and then we can use the index to look up the appropriate value in the list. Of course, it can't be just a plain old list, because we have this gamma here, which is a list of types, and they might all be different. So the environment needs to be able to store at different positions. It needs to be able to store different types of things, right? It might have to have a number in the first position and then a boolean in the second, and plain lists don't do that. So we'll define better lists. And I'm going to call this, in the spirit of calling things names, which suggests that they're proof things, and then not treating them like they are, I'm going to call this thing all. So it'll take an implicit type A, which is going to be the type of the elements in the list that we want to index over, so gamma in this case. And it's going to take a P, which is totally not a predicate over A. And then it's going to be not the predicate over lists of A. And if you're reading this as a proof, it would say this predicate holds for all the elements in the list. But we're not going to read it as a proof, so it'll be, for every element of the list, it'll be a list of P's of the corresponding, at the corresponding index. So there'll be an empty list.
2 brackets, or is
that is a justified question, but it is just 2 brackets. Sorry? This is Monaco, I think. I believe, I couldn't swear on it, but I think it's Monaco. And notice also, I don't think I mentioned that constructors can have the same names as other constructors. So this is the empty list in the all data type, and here the index is the empty list of the list data type. It's type checking. So at type checking time, it checks what type are you expecting, and so in this case, for instance, all expect a list as the second argument, so it knows it has to be the list nil. If it doesn't figure it out, and you have to disambiguate manually, you can say list dot to qualify it. Yeah, but with underscores, right? So it's an infix operator. So it's the actual name is underscore in underscore. But yes. Okay, so that was the nil case. That was easy. What about the cons case? So we are going to need some implicit stuff. X and X is for the head and tail of the list. But once we have that, what's this list going to contain? Well, it's going to be a P of X and then an all P X's. So it's going to have a P of X at the head. So the underlying list, the context in this case, in what we're going to use it for, starts with an X. And so what this list should start with is a P of X. Or it'll be a value of X. And then the rest of the list is just all P X's, and that'll give us. So another thing I should mention that could bite you is that Agda is a bit picky when it comes to white space. So if I don't put a white space here, for instance, it'll get terribly confused. Yeah, sorry. Sometimes it says, did you forget a space? But not always. So there's no in Agda, there's no restriction on what characters you can use in a name versus an operator or things like that. So when you, which means that you're going to have to, space out things. If you want to say X plus Y, and you write this, then to Agda that's just a name of an identifier. Sorry? These are proper underscores. Yeah, this is ASCII underscore.
Ulf,
Yes.
the microphone.
The microphone, but I don't think it works. Does it work?
Yeah.
Does it make a difference?
Yeah, for recording.
Oh, I see. Oh, it's just because I didn't. Okay. How long it's been off? A few minutes. Okay. There'll be a gap in the recording. Okay. So do we like this new list type? Yeah? Well, I don't know. Yeah, we haven't actually seen it in action. Maybe we can't actually use it, and then it's kind of pointless. But yes?
Why don't we just have a function from indices to values?
Yeah, we could, I guess. It might be a bit awkward to work with. For this, I guess it will work. When you get to lambda calculus, extending a list with one element is kind of straightforward. It's just cons. Extending a function from indices to values with an extra thing, it's not super awkward. You could. It's often nicer to work with first order structures than higher order. But certainly that's also an option. But this is kind of a useful type of list. So how long am I going, Zina? Is it 15:20? So how long am I going? 15:20-ish. Yeah. Sorry, yes, 3. I'm European. Okay, so what? We still have a hole here. Oh, and we also didn't use. Let's define env from a context to a set to just be env is all value gamma. So we're saying an environment for gamma. Well, it's just a value for each element in gamma. And then we're going to need to put environments here. And then let's do search replace. Like so, okay. So now we're in this position. In the var case, so we have, we're supposed to deliver a value t. So you notice there's some dots in front of some stuff, and that means it's not something you can refer to because you haven't named it yourself, but the type checker really wanted to talk about it, so it made up a name, but it put a dot in front of it to just indicate that it's not in scope in your world, but it's in scope in the type checker's world. So you look at the context, you'll see you have dot gamma, which is a list of types, and dot t, which is a type, and then some stuff which mentions dot t and dot gamma. If you really wanted to refer to these, you can name them by saying things like this. So you give curly braces, and then you say, the name of the thing equals the name you want to give it, and often that's the same name, but just to illustrate, I gave it a different name, and now you get n is of type n gamma, and x is t is in gamma. Yes.
So in Agda, the dot pattern, the dots are also used in the constraint pattern.
Yes.
And normally it's okay because when you see it in the context type, you don't confuse it with the dot pattern, except when you try to do case analysis and it brings. Is there any particular reason?
Yes. Is there any particular good reason behind it? Maybe not. I mean, the reason is there's a very restricted set of ASCII characters that you can use to punctuate things without, eating up all of the ASCII operator. You want to use plus as the function plus, right, and not. So dots are a bit overloaded. What changed was that now it says gamma here, and it's also not saying dot gamma, which means in the goal here, I can actually, I can put something in that mentions gamma explicitly. No. So they're implicit. So you didn't name them, so you can't. If you want to talk about them, you name them. But the whole point of the implicit argument is that you don't want to talk about them. You want, right? You want them to be, hidden away, and let the type checker worry about them. You notice here we never mentioned a or gamma in the code here. Yeah. And if we were calling another function, it would probably be implicit for that one too. But so occasionally it happens that you want to talk about them, and then you bring them into scope. Okay, so let's go back to this one. So we have the pieces that we need, right? We have an index into gamma, and we have an environment over gamma, which is a list of values, one for each type in gamma. So that should just be a case of looking up that index in this list. Yeah. Of course, we don't have that function, but let's define it. So I am going to call it look up. And this is also an exercise, by the way. So if you follow along now, the exercise will be easier. So it will take some implicit stuff, the A and the P. It should take also X in A. Well, I probably don't have to name those or type those. X and X's, and then we're going to have a list of P's, one for each element in x's, an index into x's that says somewhere in there there's an x. And what we should be able to do with this information is extract the p for that at that particular position in this px's. Some people are looking mystified. So if you forget about the fancy types, what we have here is, you're given a list of p's, you're given a natural number, and you're supposed to pick out the nth element of the list. And all the other stuff is just extra type information that we have lying around about the structure of the lists and the indices. So what should we, any suggestions on how to proceed? There are two choices, right? P's or I's, or I. But let's do yours, because it'll be more interesting, and then we'll do the other one because it's nicer. So I case on P's, and then it decided it wanted to call that guy x2. So rename it to P. Why don't we do the second case first? So the list is p cons p's, and we have to index it at I. Well, it would be nice to know whether I is 0 or successor. So I'm going to case on I, and it's either 0 or successor. So in the 0 case, well, when I index p cons p's at index 0, that's going to be p, and fortunately it seems that that's also type correct. So I'll just do p here. And in this case, well, I want to index p cons p's at index successor I. Well, it's not going to be the first element, so it should be one of the later elements. And we have exactly the things here to be able to call lookup just recursively on p's and I. P's I. Good. Now we have this third kind of troublesome case. Yeah. So we're supposed to provide a p of x, right? But the list was empty. There were no p's. So that's bad. How are you going to, there's no p we could return. So that's a bit awkward. Instead, we have this thing here, this I, which says x is a member of the empty list. So I is an index into the empty list. I would really, really like to see that I. That'd be very interesting. So why don't we pattern match on I? It's going to be interesting to see what constructors pop up. Yeah. So I'll do that. And then it says, well, actually, no. There's no such thing. Move along. So what happened was I pattern matched on something where no constructor would be type correct. And then it said, well, okay, there's nothing, that we could never have a value of this type, so you don't have to, this is an impossible case, don't worry about it. So we don't have to give a right-hand side here because there's an impossible case, and these empty parens means it points out here's the impossible guy. Well, if I run it, it's going to run fine. It's going to hit one of those two possible cases. You know, it's not going to. If I run it, we're not going to hit the. It's impossible. So it's.
No, but what happens if you now, for example, if a list is for elements at the fifth one?
Yeah, but that's not going to be type correct, right? Well, it's not going to be type correct. You're not going to be able to. That's the whole point of the exercise, right? That these kind of natural numbers are indices that are really indices into the list. They're not. You can't say, oh, pick the fifth element and the list only has 3. There's no way to build a well-typed element of that type. Yes?
Are there times where you have an impossible case like this where it's difficult to prove to Agda that it really is an impossible case?
Well, it depends on what you mean. So in this case, the notion of what is an impossible case is kind of restricted. It doesn't mean there's no inhabitant of the type, because that's undecidable. So what it means concretely is there's no constructor pattern you could put there that would be well typed. So sometimes you say, well, this is an empty type, but you could still, suppose you wrapped an empty type in a new data type with one constructor, you wouldn't be able to say that was impossible, because you could put the wrapper and then X. That would be well typed. It's just that X would be the impossible.
So that syntax has that very specific meaning that
Yes.
there is no constructor for that.
Yeah.
Then why doesn't it make no together? When you point out case 2 there,
Well, sometimes it's not trivial, right? Sometimes you have to sort of do some pattern matching, and then it turns out. So in this case, we had to first pattern match on the empty list. And then we found out that, well, actually the index, in the empty list case, the index can't actually, there's no value for the index. But we had to pattern match on the empty list to find out that, yes?
You can, though, if you pattern matching on the integer index first, and then pattern match. So sometimes if you do it the other way around, you won't ever get that case.
Yes, which is what that was my essence.
Oh.
That's what I said.
Oh, sorry.
We'll do it the other way around. So, but the empty params is there because it's not possible to, in the general case, decide what cases are impossible and not. Because you could have to do arbitrarily deep pattern matching in order to find these empty params where they should go. But in this case, as someone pointed out, we decided to match on the list first. Oops. But we could also pattern match on the index first. Yeah. And then we get 2 cases. It's 0 or successor, we know that. But now, so the thing about these constructors is that both target non-empty lists. There's no constructor targeting the empty list. So in this case, where we say, okay, the index was 0, what is P's? Well, it has this type, right? All P X cons X's. So when I pattern match on P's now, well, there's not going to be a case for the empty list because we know it can't be the empty case because the type is the index is a cons. So I pattern match on that, and it just gives me the cons case. And then this goes through as before. Yeah? And doing it that way gets rid of this impossible case. So in this case, Agda can figure out that if you just pattern match on this guy first, everything will work out. You don't need the impossible case. So then we can just use that here. Okay, so say look up x in n, and you're good to go. Yes?
Is there a way, let's say you didn't know what you wanted to master look up, is there a way you can generate possibilities?
Yes. Well, so what you can do, well, there are a number of things you can do. You can say, I know I want to apply lookup in, but I don't know how, what the argument should be or how many. Then you can hit Control-C, Control-R for refine. So you type in the name of the function you want to apply, and then you hit refine, and it will give you the appropriate number of arguments to fit in that. You could also try proof search, which is Control-C, Control-A. And then you need to give it, say, you're allowed to use the function lookup in. So by default, proof search won't use any defined functions. But if you do that, then it comes back and say, well, there's no use way of doing it. Like this. Maybe we should run it. I don't know. Bob, did you have a question? Did you have a question? Or
What is the key step for filling the hole?
filling the hole, it's Control-C, Control-Space.
Control-C.
Control-C, Control-Space for just giving the thing the exact thing that you. Yes, you can. So if you want to run something, you can run, evaluate expressions or terms from inside Emacs. It's Control-C, Control-N. So we could run this eval. Let me type out. So let's have an environment. See if we can figure that out. Which says, we probably have to, let's see, 5 false. No, it didn't like that. So that should be not, bool. Oh yeah, I didn't like that because I have several falses in scope. There's the bool false and there's the expression false. And then let's have an expression over gamma of type nat. And it should be var suc0 var 0 and lit phi var 0 plus. Okay, so this turns out to be well typed, so that's good. We could see what happens if we make it not well typed. Then it says that's not well typed. I wanted something of type x per nat over here, but you gave me something of type, well, it doesn't say what the thing was, but it says bool is not nat. So our type error messages could be better, I admit. But at least it catches that I tried to give it an incorrect thing. Okay, so Control-C, Control-N, and then it wants you to type in something to run. So I say eval NV, and this, I think, will come back 5. No, it'll come back 9. 9. Fantastic. So it seems to work. Okay, so Control-C, Control-N. And then you can also, of course, write the main function that prints something to the terminal and compile it and run that, as you saw in the lambda example. So I wonder what I should do. Let's do this. So we had all, and then we had this in function, which was this index thing. You can generalize this to be sort of have the same shape as all, same type, in fact. And call it any instead. So we define this in thing, which says somewhere in the list X appears. What this is going to say is somewhere in the list there's an element that satisfies P. Or I have a P of X for an element X in the list. So what it's going to be is it's going to be not quite a natural number, but a natural number where we have a P at the end. So let's do the 0 case. So before we just said in the 0 case of in, we just said, well, X is at the head of the list. But this guy is going to have a P of X there as well. That was the old type. So any P X-axis like this. And successor, well, it's going to say, well, it's not going to be the head of the list that satisfies P. Well, it might, but we don't care if it does. But we're going to have a P of X for some of the X's further down the list. And then we can actually, using this type, we could define in. Let me give a different name to it. So that was
prime or an apostrophe?
That's actually a backslash prime.
Okay, so it's actually a prime, not an apostrophe.
Yeah, it's actually Unicode prime. Yes, I'm sorry. Yes. Copy this. The underscores means you can use it as an infix operator. So you know, like we saw here, I'm saying X in X's, and that means the same thing as underscore in underscore applied to X and X's. So it's just the way we do infix operators.
The infix notation can just say as it is
You don't have to, but if you don't, then you get some default level which you don't know what it is exactly. Well, I guess you could find out, but okay, so I will define this. So what does it mean for x to be in x's? Well, it means that somewhere in the list x's there's a y that satisfies the predicate of being equal to x. So we can do that like this. So this triple equals, this is the built-in identity type of Agda, which has the one element raffle that is a proof that x equals x for any x. And now I'm using, this is an infix operator, but I'm using it, I want to apply it to just one element. I could do it with a lambda as well.
Could you use Haskell's like full text with the X underlined?
We don't have sections.
Okay.
No. But I could write that. So actually in the exercises, this is how I defined in using any. So that makes, when you define this function, for instance, there'll be a little proof object here, proof of equality, as an argument to 0. But that's actually all I was planning to do for this session. So any questions right now? Otherwise, I think we'll just, is there a break of some kind, or do we just go straight into hacking? Excellent. That was my next question. Is there coffee? So thank you.